So in this example, we have 4 vectors, and all 4 of these vectors are vectors in the xy plane. And the question is this set of 4 vectors? So there's a little bit of a terminology thing where I think Lei could do a better job in writing this question. Whether the set of vectors is linearly independent. So in other words, all 4 of these together. Is it possible? So we're going to end up translating this into a question about a linear system of equations again, as we always do, right? It's going to come down to a matrix that we could row reduce and find our answer, right? But again, we want to know if it's possible for these 4 vectors to be linearly combined, 5, 1, 4, 8, 1, 4, and negative 1, 9. Is it possible to linearly combine these 4 vectors, and let's call the coefficients x, y, z, w, say. And if I'm asking if they're linearly independent or dependent, then by definition, what am I going to put on my right-hand side? The 0 vector. And we are going to answer in the affirmative that they are linearly independent if what happens? Well, I guess my point is, what would the solution of this vector equation have to look like if these were linearly independent vectors? Trivial. If these vectors, by definition of linear independence, if these vectors are linearly independent, then that must mean that only the trivial solution solves this vector equation. In other words, x, y, z, and w would all be forced to be 0 if these vectors were linearly independent. But if there exists any other solution, any non-trivial solution, then these vectors are linearly dependent. And again, we're supposed to do this by inspection, but I wanted to do it kind of longhand to illustrate the point of how it works. That if there is a non-trivial solution, then these vectors must be linearly dependent. But because we're asking a question about a vector equation, this vector equation is what's at issue here, let's turn that vector equation into an augmented matrix. And what would that augmented matrix look like? Okay, so on the left-hand side, 5, 4, 1, 8, 1, 4, negative 1, 9. On the right-hand side, zeros. So there's our augmented matrix that we could then solve, right? We could find a solution set for it that will tell us what x, y, z, and w are. We don't care exactly what that solution is. We just want to know whether that solution is unique or not. Because if the solution is unique, then only the trivial solution works. But if the solution is not unique, it means that there are some non-trivial solutions. So what's going to tell us? What are we looking for in this row reduction to tell us how many solutions the system has? Without actually doing out the row reduction, what would we be looking for? How many pivots, right? And for this system of equations, how many pivots are there? At most. We can only have 2 pivots. There could be 1, but there's definitely not any more than 2 because we can't have more than 1 in a given row. So if there's only 2 pivots, and maybe they're at these positions, I don't know. I mean, we would have to actually do the row reduction to figure out where they were. But if there's only 2 pivots, what does that imply about this system? How come? Why does that imply it has to have a non-trivial solution?
Because the other 2, C and W, are not an equal, an actual number.
Right, z and w are not going to be bound to the value of anything. Z and w are going to be free variables. Because remember, every column without a pivot in it corresponds to a variable whose value can be selected freely, which is going to give rise to non-uniqueness of solutions. Free variables exist, therefore a non-trivial solution exists. So what's the inspection that they're talking about in the problem? By the way, that means that choice A and choice B are definitely out here. So this system, this set of vectors, is definitely linearly dependent. But how could inspection have told us that?
Because of the pivots.
Right, that's the pivots thing. Because we have 4 vectors, and so our matrix equation is going to have 4 columns in it. But every vector only has 2 entries. And because there's only 2 entries in each vector, our matrix equation is only going to have 2 rows. And because there's only 2 rows, we can only have at most 2 pivots. And there are too many columns for those pivots to go in every column. Because when the pivots go in every column, the solutions are unique. But if there's any column without a pivot, that gives us a free variable, and therefore the solution is not unique. So the best answer here is D. It's linearly dependent because there are 4 vectors, which are going to give us 4 columns in our matrix. But there are only 2 entries in each vector, and therefore only 2 rows in our matrix. So we cannot have a pivot in every column. Therefore we have free variables. Therefore the solution is not unique. Therefore, the vectors are linearly dependent because there's a non-trivial solution to this homogeneous equation.